So in this last lesson, we're going to be looking at some of the different characteristics of stars, and we're also going to be looking at the life cycle of stars too. So I'm going to jump around a little bit. We're going to talk about stars. It's probably the biggest thing that we talk about. Your last lesson, you took a really brief look at the sun yourself, the different layers. Just a reminder that the sun itself is a star. So everything that we talk about here is actually going to apply to the sun as well too. So let's talk about what a star is. A star is a hot ball of gas that emits energy in the form of light. So stars are luminous objects. They're actually able to give off their own energy, and that energy looks like light. How do stars differ? They can differ several ways. They can differ in brightness, they can differ in color, and they can also differ in temperature. So let's take a look first at the characteristic of color. Stars can be three different colors. They can be blue, they can be yellow, or they can be red. So you can see a couple different examples in this photo from space. You can see some red stars here, some yellow stars here, and then you can also see some blue stars up here and down here. So that's one way stars could look different. When you actually get a really good picture past our atmosphere from space, you can see stars are actually these three different colors. Stars can also vary in what's called luminosity. Luminosity is how bright a star is. So luminous objects appear brighter when they are closer. So something that looks really bright in the sky is probably closer to us. Something that appears really dim in the sky is further away. So it's going to appear brighter because that light is stronger, right? Stars give off light, it looks brighter, whereas something that's far away, you can't see the light as well. There's actually two things that affect luminosity. We call these apparent and absolute magnitude. So let's talk first about apparent magnitude. Apparent magnitude is how bright a star appears from Earth. So let's say that you're standing on Earth and you're going to actually just look out and you're going to judge the stars. Here it looks like star number 3 is the actual brightest. Star number 4 is the second brightest. And these two, 1 and 2, are really hard to see. So we would go ahead and say that these are the least bright. So stars can appear to be the same brightness to us on Earth, even though they might not be, and let's talk about why. So to talk about why stars might not be as bright as they appear to be, we have to understand what absolute magnitude is. So absolute magnitude is the actual brightness of the star. So that's taking away how far away it is from you. If they were all lined up equally, how bright would they be? So if we look at absolute magnitude here, we can see that star number 5 here is the actual brightest. Star number 4 is the other brightest, and star number 3 isn't actually that bright. Stars that are as bright as the sun have a luminosity of 1. If the star has a luminosity of 50, it's 50 times brighter than the sun. So we kind of use our sun to compare. We rated a 1. Anything that's a 2 is twice as bright as the sun. 3 would be 3 times as bright as the sun. So the reason that absolute and apparent magnitude can be different has to do with distance. So here we've taken distance out of the factor. This is absolute magnitude is how bright a star actually is. And you can see 5 is the brightest. But maybe in this picture here, 5 is actually the furthest away. Or let's take a look at 4. In this picture here, maybe 4 is further away, so it doesn't appear as bright as it possibly could be. Another thing that can vary with stars is you could have the stars vary in temperature. So we have different types of stars. We have hot stars, we have cooler stars. Hot stars are said to be around 15,000 degrees Celsius and greater, so they are extremely hot. A hot star we would put about here. So the temperature of the star actually determines its color. So you can see the hottest star is actually blue, and you can see the coolest star is actually red. So that's kind of the opposite of what you would think, right? When you turn on hot water, you turn on the red tap. When you turn on cold water, it's a blue tap. Here it's the opposite for stars. So the hottest stars actually appear blue. The coolest stars actually appear red. Our star, our sun, is right about here. It's a yellow star, and it's about 6,000 degrees Celsius. There's a relationship between temperature and color. We just talked about it. Color indicates a star's surface temperature. So we know that blue stars are hotter, and we know that red stars are cooler. So we don't necessarily have to measure the temperature of a star. We can just look at it and tell whether it's hot or cold. We can look at it, and if it's blue, it's hot. If it's red, it's cold. If it's yellow, it's somewhere in the middle. There's another relationship between luminosity and color as well too. So luminosity, brighter stars are said to be blue and dimmer stars appear to be red. So if you're looking up at a sky and a star appears blue, you know it's got a high luminosity. It's going to be very, very bright. And if you're looking up at the sky and you see a red star, it's going to have a low luminosity. So that means it's going to be dimmer. So again, you can actually see how bright a star is based off of its color as well. So color is a great indicator of all these characteristics of stars. The last relationship is between size and luminosity. So there is a relationship between size and brightness as well too. Bigger stars are actually brighter. They have more energy to give off. They have more gases to give off, and smaller stars are dimmer. So if you look up in a sky and you see a really, really, really bright star, it's probably large. If you see a smaller star, it's probably dimmer. Let's talk a little bit about the composition of stars. So what are stars actually made up of? First of all, you can imagine it's pretty hard for us to measure stars and what they're made up of. So we use something that's called a spectrograph. So a spectrograph allows us to measure the spectrum of a star. Spectrum of the star is just like a light spectrum. So you can actually see the different light spectrum. From those lights, scientists can determine what elements are present. So they can actually use a spectrograph to go ahead, identify the different light colors given off by a star, and they're able to go ahead and tell us what elements are present for that star. Now that we know a little bit about stars and their characteristics and their composition, I want to talk about what's called the life cycle of a star. So we want to talk about how a star is maybe born and what happens to the star at the end. So let's talk about star beginnings. Star beginnings, we say that all stars actually begin as a nebula. So all stars are born as what's called a nebula. A nebula consists of dust and gas. As your nebula grows, your mass is going to grow. It begins to cycle, and it begins cycles of heating up, spinning, and contracting. So that nebula gets hotter, it spins, and then it contracts. And then when it contracts, the mass is greater, it gets hotter, it spins, and it contracts. So it's kind of taking all of these gases, and it's slowly compacting them into a little hot, dense ball. As the temperature increases, the core is going to begin to glow. So the hotter it gets, the more the core is going to glow. We actually call this a protostar. Proto kind of means first. So the first kind of beginning of a star, we call that protostar, and that's that nebula that's come together, that's spun around, that's heated up, and it's starting to glow. The core of a protostar's temperature rises and nuclear reactions begin. So this was from your sun note. We talked a little bit about the fact that the energy that's given off by a star comes from nuclear reactions. It's mostly from helium decaying to hydrogen. So those reactions are actually chemical reactions, and it's helium decaying to hydrogen, and that's what gives up a star's energy. And remember that energy looks like light. The star mass evolution. So this is a really fancy way of saying that the life cycle of a star is determined by its mass. So depending on if it's a big star, a medium star, or a small star, that's going to determine what it kind of can become to be and what its remains are going to be. So let's take a look at our three categories. We're going to look at a low mass, a medium mass, and a high mass. So essentially a small, a medium, and a big star. You can see that all of these stars actually start as nebulas. So no matter if you're big or small, all stars started as nebulas, which is that dust gas cloud there. What's going to vary is the length. So you can see that a small star can live for about 100 billion years, whereas a large star only lives for about 7 billion years. So large stars are giving off way more energy. That means they have a much shorter lifespan. So large stars have the shortest lifespan. Small stars have the longest lifespan, and medium stars are right in the middle here. The first stage of the star, so this is the first stage after the nebula that the star starts off as. We categorize a low mass star as a red dwarf. So remember, red means a little bit cooler, red means a little bit less bright. So all of that really kind of makes sense with a low mass star. And we call it a dwarf because it's a smaller size star. A medium mass star, we call it a red giant. And a high mass star, we call it a red supergiant. In death, so after it's passed through its life cycle, right when it's close to death, that really just means running out of energy, we call a low mass star a white dwarf. We call a medium mass star also a white dwarf, whereas a high mass star is so big, it actually turns into what we call a supernova. The remains is when it's totally out of energy, what's going to be left, right? When it's totally out of energy, it's not like the star is gone. You can't destroy matter. There's going to be something left. So for a low mass star, we have just what we call a black dwarf left. For a medium mass star, we call it a black dwarf. And for a high mass star, it's so big and it's left behind so much matter, we call it either a black hole or a neutron star. So high mass stars can form either a black hole, which you might have heard of before, or a neutron star. Let's look a little bit at the difference between a neutron star and a black hole. So after a supernova, there's two possible outcomes for the remaining core. So the two possible outcomes for the remaining core, those large stars, when they are left behind, their remains could become a neutron star. What a neutron star is, it's a compressed atom from the star's core. It's made of the densest material and it's known to be about 15 kilometers across. So a neutron star is just a really, really, really dense core that's about 15 kilometers across. A black hole on the other hand, that's going to form when the star was more than 40 times the mass of the sun. So black holes only form when we have really large stars, about 40 times larger than our sun. That's their remains. The effect of gravity in a black hole is so great that all matter falls into a single point. So essentially, a black hole is so dense and gravity is actually sucking everything in towards it. It's sucking it in towards a single point. So a lot of things can get pulled into the gravity of a black hole. So a black hole is not actually a hole. It's just a really, really, really dense mass that's got a really high gravity that's pulling things into it. Now, these can be confusing with stars because we know that stars are related in brightness, color, size, how long it will live. So all stars can actually be arranged on this graph. We call these the HR diagrams or the HR graph. And this is actually what most stars look like. And it kind of shows you the relationships between a hot star, a cold star, the size of stars. And you can actually see that stars exist on the spectrum. So if we're looking at a really, really, really hot star, we're looking at a blue star. So you can see all of our hot blue stars are going to live on this side here. Most of them are larger. Some of them are really large. So this main sequence is where most stars fall. And then you can see we kind of have these exceptions up here. So we have what's called a blue giant, that's over here. And then we have our blue stars that are in our main sequence. And we have our white dwarfs down here. White dwarfs are smaller stars that are still hot. They're still kind of on the bluer end of the temperature, but they're much smaller than we would think that they would be. So they have a lower luminosity. In the middle of our spectrum, we have exactly what we would think, right? In the middle of our spectrum, we would have, oh, there we go. In the middle of our spectrum, we would have yellow stars, and those yellow stars are about a medium size. And then down here on the other end of our spectrum, this is where we have our cooler and our red stars. So our cooler and our red stars are said to be smaller. So they're smaller on this side here. We do have a couple cool red stars that could be larger, and those cool red stars, we call them red supergiants, or we call them red giants. So this diagram actually kind of shows you just where stars might fall, and it shows you how stars might be related in terms of temperature, in terms of color, also in terms of size. So most stars actually fall in this main sequence, but we do have some exceptions over here. So stars in the main sequence are in the stable part of life. Stars outside the main sequence are said to be near their end of the life. So these white dwarfs, these blue giants, these red supergiants are near the end of their lives. That's why they're kind of the exceptions. Whereas anything that's in the main sequence is in the stable part of its life, and it's still got many, many years to live. So that's the life cycle of the stars. All of this information can be found below in writing as well too. And there's actually a really great video about stars. It's about 10 minutes that I recommend you watch as well too. That's it. That's everything that we are going to cover in space. So obviously it's a very large unit and we did not spend a lot of time on it. So hopefully you have lots of questions, which is great. And I really hope that you include some of those questions in your summative assignment. Any questions, let me know. And otherwise, keep working hard. We're almost done the semester. All right, have a great day, and we'll see you guys later. Bye.